space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
They've intrigued man for centuries, captivating astronomers and astrologers alike. A mysterious alignment between the Great Pyramids of Giza and the stars of Orion could have been more than a coincidence. And instead of 12 zodiac constellations, we actually have 13. What is our 13th sign, and why was it forgotten? The patterns that once navigated mariners across treacherous waters now guide astronomers to uncover the mysteries that lie within the constellations.
Before the internet, before movies, the night sky and the constellations were the greatest show in town.
This gallery of stars forms more than just pretty pictures. It contains an enormous sampling of star types. Through constellations, we can learn a lot about the galaxy and the universe beyond. Before we had high-tech navigation devices, GPS, or even compasses, we had stars. Like landmarks along the road, constellations can help us find our way. They give us direction, distance, and a sense of where to go.
So on Earth, when we want to tell where something is, we give its coordinates in latitude and longitude. And what that means on Earth is it's a measure of, latitude is a measure of the distance between the North Pole and the South Pole, and longitude is the east-west distance, so the other direction. Similarly, we have a celestial coordinate system.
But the coordinates, they're not called latitude and longitude. They're called declination and right ascension. They are just direct extensions of latitude and longitude on Earth, projected out into the sky.
Ancient navigators used this imaginary grid to plot stars and orient themselves across the seas.
Not a precise kind of indicator of direction, but certainly a cue to keep people reminded of what the broad pathways through the seas might be.
By using a sextant, mariners were able to use guide stars like Polaris to navigate.
This is a sextant. It's a tool used in celestial navigation. Once a celestial body hits what's called its lower limb to the horizon, you'd mark the position. Using the time and the numbers on this sextant, you can then use it in fixing your position at sea.
Today's navigation uses man-made stars, satellites.
With the use of our man-made stars, per se, our GPS positions and differential GPS, we're able to fix the ship's position within a few yards, instantaneously, anywhere we are in the world.
Now that GPS has replaced sextants, celestial coordinates are more important to astronomers than they are to sailors. Even though the coordinate system gives them an idea of where to point their telescopes, the grid falls short in a serious way. It assumes all the stars are all the same distance from us, an assumption that's flat out wrong.
When you look at the stars in the night sky, they all appear to be about the same distance away, as if they were in the same plane. The same happens when you look at a city skyline from a distance away, such as we are from the Chicago skyline. So while those buildings look like they're the same distance, they're really at many different distances away. The same is true of the stars. While they all look like they're at the same distance, some are close, some are much further away.
So how do we know which stars are close and which are far away? As it turns out, that's the most difficult question of all.
That's been the single greatest frustration in all of astronomy. Looking at the night sky, even with telescopes, you cannot tell distances. That's been the holy grail of astronomy for centuries.
We're here in the Angeles National Forest, and I've got with me a handy trail map. And I'd like to take a hike, maybe going to, say, Switzer Falls, which on my map looks like it's not very far, only maybe a mile. But the trouble is, I could badly underestimate the difficulty of this hike because my flat map here fails to take into account one very significant factor, which is the elevation. So, in fact, my simple 1 mile hike could turn out to be a 5,000-foot climb. So does my constellation map fail to tell me about the true distance between two stars. Even though in a constellation they might look like they're right next to each other. In fact, one could be much farther away than the other, and I would never know it if I just looked at the celestial coordinates only.
Like hikers in the woods, astronomers rely on clues to help them gauge the distances in our vast and mysterious universe.
So when we're hiking in the forest, even if we don't have a map that tells us elevation, we can use our knowledge of the local topography and types of trees to tell us something about our altitude. For example, certain trees prefer lower elevation, whereas other trees prefer higher altitudes. Similarly, astronomers use certain types of reference stars as guideposts, familiar guideposts, as a gauge of distance.
The first tool in the astronomer's kit is the phenomenon of parallax. It's something we use on a smaller scale every day to see the world in 3 dimensions.
The way to think of parallax is a very simple exercise that everybody can do. So take a look at your finger and look at something really, really far away. If you use your right eye and line up your finger with a distant object and then use your left eye, you'll see that your finger actually appears to move quite dramatically.
This apparent shift is caused by the distance between our 2 eyes.
Astronomers measure parallax by looking at a star at one position and then looking at it again 6 months later when it's moved as far as it could go from our vantage point. 6 months is really when the Earth is as far away from that original position as it can be.
The closer the star, the greater the parallax. The problem is that stars aren't very close. Even the parallax angle of our closest star, Proxima Centauri, is difficult to measure.
It's less than a second of arc. What's a second of arc? There's 360 degrees in a circle. In every degree, there are 60 minutes of arc. And in every minute of arc, there are 60 seconds of arc. Proxima Centauri has a parallax of 0.7 seconds of arc, so it's very small.
To span the distance to more far-flung stars, astronomers count on a familiar guidepost to lead them. Much like the Coast Guard uses a lighthouse.
The men and women of the Coast Guard know that every lighthouse has a particular pulsation frequency. One might flash 2 times a minute, another 4 times. They can use this to determine exactly their position, just based on the pattern. In the same way, astronomers can use a cosmic lighthouse called a Cepheid variable star.
The constellation Cepheus, named after the mythical king of Ethiopia, claims 57 visible stars, including Delta Cephei, a variable star that is the prototype for Cepheid variables. By a quirk of nature, Cepheids keep time like a metronome. The bigger and brighter the Cepheid, the slower it will pulsate.
So what you do is find a Cepheid variable, measure its pulsation period, it might be 10 days or 60 days, and then you've got a standard candle. You can determine how far away that star is.
A standard candle is a basis of comparison, a star of known luminosity and distance that we can compare similar stars against.
You know, a light bulb gives off the amount of light it gives off, a certain amount of watts. But that light is going to look a lot brighter if you're right up close to that light bulb than if you are 10 feet away. And so the luminosity of a star doesn't change. You know, that is what it is. But apparent magnitude, you know, depends on where you are, how far away you are, whether you're right up close to something or you're seeing it from the other side of the street.
If a Cepheid doesn't appear that bright, then it must be far away. Astronomers can calculate how far it is based on how dim it appears.
Looking at my Cepheid variable and plotting the light curve, how long it takes to go from brightness to dim to back to brightness again, tells me what the intrinsic brightness of that star is. So I can calculate distance to variable stars by observing the period of their variation.
That's how Edwin Hubble was able to determine that Andromeda was 2 million light years outside our galaxy. But Cepheid variables have their limits. To measure distances far beyond Andromeda, astronomers rely on supernovas.
It turns out that supernovae can also be categorized as standard candles. Type 1a supernovae are all the same throughout the universe. We know how to calibrate them. And that's how we determine the distances out to the Big Bang and the very edges of the universe.
Peering into the Big Bang, scientists can nearly see the beginning of time. 300,000 years after the Big Bang. Even our most familiar constellations have a lot to teach us about the cosmos. Orion, which is Greek for hunter, has 77 visible stars. Alnidak, Alnilam, and Mintaka make up the 3 stars in Orion's belt. In modern times, astronomers have hunted Orion, finding a variety of astonishing objects.
When I see Orion, I also see the life and death of stars. Just below the belt, there's a little smudge called the Orion Nebula, and that's a nursery for baby stars, and you can actually see that with the naked eye.
Orion has also bagged a pair of stellar gems.
If you look at the upper left-hand shoulder of Orion, you see the red giant Betelgeuse, and if you immediately look right down to the lower right star, the star that's sort of his leg, you'll see the blue supergiant Rigel.
Betelgeuse, as a red supergiant, is a star in its death throes.
A red supergiant is a star that is actually quite a bit cooler than our sun, but much, much larger.
Betelgeuse is 14 times more massive than our sun. When it runs out of nuclear fuel, Betelgeuse will become unstable and implode in a colossal supernova. It can detonate at any time.
And when it explodes, it will light up the entire night sky, and it will even be visible during daytime. And maybe it's already blown up. It's 427 light years from Earth, which means that perhaps it has already exploded, but light hasn't had time to reach us yet.
The supernova will draw more attention to a sky that's been captivating us for thousands of years. The ancient Egyptians consulted the heavens to tell them when to plant and when to harvest. Every star possessed a sacred meaning. They called Sirius in the constellation Canis Major the star of Isis. Sirius's appearance before dawn during the summer solstice forecasted the annual rise of the Nile River. Other constellations, like Orion, might have had a certain architectural significance.
Egyptologists have often asked the question, why did the ancient Egyptians build 3 great pyramids that are slightly misaligned? Did they have bad ruler sticks thousands of years ago? The 3 pyramids seem to be aligned to the 3 constellation stars of Orion.
What does this alignment mean? Was it a coincidence, or were the pyramids intentionally engineered this way? The pyramids of Giza seduce us with archaeological mystery and historical intrigue. Some scientists think the pyramids have a certain astronomical importance.
It has been claimed that the layout of the 3 major pyramids on the Giza Plateau, including the Great Pyramid, are set on the ground to mimic the 3 stars in Orion's belt.
It's one of my favorite connections between events on Earth and events in the sky.
But the ancient Egyptians didn't see a hunter in Orion like we do. They saw Osiris, god of rebirth. Some speculate that air shafts within the Great Pyramids were specifically designed to catapult the souls of pharaohs to the heavens.
In those pyramids, we have two different shafts. And those shafts, one points north, one points south.
The south shaft points toward Orion.
So the soul of the pharaoh would be launched through that shaft in order to be connected to Osiris, Orion, and be resurrected again, enjoying eternal life.
But others are a bit more skeptical.
In order to make it match correctly, you have to flip it upside down on the ground or in the sky. That the Egyptians did place an importance on north and on south in the pyramid. And it doesn't make any sense to say, well, yes, they lined the stars up right, but then when it came to mapping on the ground, it was perfectly okay to flip everything around and make it upside down.
The north shaft points toward one specific star.
The one pointing north points to the pole star at the time, 2,000 years before Christ, 2000 BC, 3000 BC, and that pole star was Thuban.
Thuban is located in the constellation Draco, or the Dragon. Draco has 79 visible stars. Thuban has been replaced by our generation's pole star, Polaris. Polaris illuminates the Arctic, governing our sky as a beacon over the North Pole. Lying in the constellation Ursa Minor, it's 2,500 times brighter than the Sun. Outshining its companion stars, Polaris A, B, and B. Although it's ruled the heavens as our North Star for as long as we can remember, its reign won't last forever. As Earth orbits the Sun, it teeters back and forth. This wobbling is called precession. If Earth was a perfect sphere, it wouldn't precess. But the gravitational pulls of the Moon and Sun tug at the bulging equator, upsetting Earth's spin.
Now the Earth is like a gyroscope or a spinning top. Notice that if I spin this very rapidly and then I move the axis, it points in the same direction. This is the Earth pointing toward Polaris, that as the Earth goes around the Sun, it always points in the same direction. However, precession is caused by gravitational interference, so the Earth begins to wobble.
As Earth wobbles, its axis draws a circle in the sky. It takes 26,000 years to make one complete circle.
The North Celestial Pole will move further and further away from the position of Polaris. In about 14,000 years from now, about halfway around its circle, it will be very close to the bright star Vega. But because Vega is so much brighter than any other star in that part of the sky, it will be a very significant north polar star.
In 26,000 years, Earth's axis, centered on the North Pole, will make one complete circle, and it will point back to where it is today. And Polaris will overthrow Vega and reclaim its title as our North Star. The closer a star is to one of Earth's poles, the more its position remains fixed in the sky. Astronomers call these stars circumpolar, meaning that they're visible all year long.
In fact, all of the constellation of northern stars, such as the Little Dipper and the Big Dipper, just go around in a fairly small circle. So the result of that, they go around Polaris without ever rising and setting. The further south you go, the more constellations actually rise, say at the beginning of the night and set at the end of the night, and so they don't have that magical property.
Stars vary in size, density, and also brightness. Instead of shining with a steady glow like most stars, variable stars pulsate, brightening and dimming in a hypnotic pattern.
A variable star is like a pot of tea. You take a kettle and put it on a burner, and it starts to expand, and then it releases its excess energy and then drops. And then it starts to build up pressure, and then it drops again.
So kind of in the same way, the variable stars' atmospheres expand and shrink with time, and this makes the star appear to get brighter and dimmer. Sometimes this happens over a matter of hours, sometimes it can be days or even months.
A special class of variable stars called T Tauri stars pulsate because they're young and unstable. Like stubborn teenagers, T Tauri stars have erratic outbursts. Except their tantrums involve a struggle with gravity.
As the nuclear forces push it outward, gravity pulls it back in, and it misses that equilibrium position, sort of like a pendulum, and it oscillates back and forth.
T Tauris will outgrow their pulsations. As they age, they'll reach equilibrium, becoming stable stars. In fact, before our sun matured, scientists think that it used to be a T Tauri.
This probably gives us our best look at what our solar system and our sun looked like when it had just formed, in its earliest evolution. And we know that, for example, that the clouds of dust and gas around these stars are very messy, and it must have been a pretty violent scene with many lunks and chunks of rock colliding into each other and bombarding each other.
The first T Tauri stars were identified in the constellation Taurus. Taurus, the bull, possesses 98 visible stars. Aldebaran, a red giant star, is the bull's bloodshot eye. Taurus is one of the zodiac constellations that lie near the plane of the ecliptic.
It's called the ecliptic plane because that's the only circle around the sky where eclipses can occur. The moon has to pass through the ecliptic, for example, in order to give us an eclipse of the sun.
It's also the path that our Earth travels along as we orbit the sun. 8 degrees above and below the ecliptic lies a region called the zodiac. Every constellation that falls within this band is referred to as a zodiac constellation.
At any given time, the sun is in a constellation of the zodiac. The sun lies between us on the Earth and a certain constellation.
Because we orbit our sun, the sun appears to move through zodiac constellations that are fixed in the sky. During nighttime, the opposite portion of our sky is lit by the sun. Astrologers linked each of the 12 zodiac constellations to the month that the sun passes through. So, in June, the sun sweeps through Cancer, and in July, it glides across Leo.
But you see, there's a problem with that. Each constellation is of different sizes. Some are small, some are big.
It takes the sun 7 days to pass through Scorpius, the smallest zodiac constellation, and 44 days to clear Virgo, the largest.
So you cannot divide the year into 12 equal pieces with 12 equally shaped constellations.
A lot of people put a great deal of significance on their zodiac sign, their sun sign. But in reality, since the Earth is precessing, the constellation in which the sun appears today is different from the constellation in which it appeared 2,000 years ago. So the next time someone tells you that you're competitive because you're a Scorpio, tell them, well, you know, today I'm really not a Scorpio anymore.
From the infamous "what's your sign" line to predicting fortunes and defining personality traits, the 12 signs of the zodiac have played a substantial role in pop culture. But where do these signs come from? And who named the stars?
We have original names for stars, in some cases that came to us from Mesopotamia. Some names were added to the stars by the Greeks and the Romans. Some of those survived, some of them did not.
With the collapse of the Roman Empire in about 450 AD, much of this knowledge was lost. However, it was preserved by the Arabs.
In fact, much of astronomy survives today because of the Arabic astronomers preserving and augmenting the calculations and work of the Greek and Roman astronomers.
In 150 AD, Greek scientist Claudius Ptolemy merged his own observations with historical writings labeling more than 1,000 stars. And out of all the constellations that cover our skies, we've learned that 12 are zodiac constellations. But in reality, there are 13. Even if we're not followers of astrology, most of us know what our astrological sign is. What most of us don't know is that instead of having 12 zodiac constellations, there are actually 13. Ophiuchus, which is Greek for the serpent bearer, is our forgotten sign. It has 55 visible stars and is home to Bernard's star, which is the fastest moving star through our night sky. Nestled between Scorpius and Sagittarius, Ophiuchus dwarfs the constellations it surrounds. Although it was one of the original 48-star patterns that Ptolemy cataloged, some scientists speculate that it might have been dropped as a zodiac sign to keep an even number of 12. Others think that precession could have nudged Ophiuchus off the zodiac. But the real answer remains a mystery. The only star in the universe that doesn't belong to a specific constellation is our Sun. Comparatively speaking, the Sun is a typical aging star with an average mass. But stars that have about 50 to 100 times the mass of our Sun are called Wolf-Rayet stars. The brightest observable Wolf-Rayet is called Gamma Velorum in the constellation Vela. These massive stars are incredibly luminous and are in their final stages of evolution.
The reason they get so luminous, that they're pouring out energy and radiation so furiously, it's actually powerful enough to push off the outer layers of the star's atmosphere. These stars literally evaporate themselves from all the heat and radiation that they're generating, leaving behind just the very, very hot central core.
Although scientists haven't directly observed the death of any, they speculate that Wolf-Rayet stars will end their lives in colossal supernova explosions, or possibly collapse into massive black holes.
But before they do, they put on a very spectacular show of blowing out all of their outer layers of gas into the interstellar medium.
Today, our network of ground and space-based telescopes allows astronomers to see any point in the sky. But ancient astronomers in the northern hemisphere couldn't see that the southern hemisphere looks out on an entirely different view.
If you're in the southern hemisphere, the most prominent feature in the night sky is the Milky Way. And in the Milky Way, you have these zones that are dark. They're dust clouds. But when you look at them from Earth, they're just dark. Against the backdrop of the very bright Milky Way and all the stars, it's the most noticeable thing.
These dark clouds appear as holes within the Milky Way's starry swath.
They're such a distinctive pattern, these holes, that some civilizations, in particular the Incas in South America, identified these black splotches, these absorptions, as constellations themselves.
These dense patches of dust are known as dark cloud constellations.
There is an amazing, complete blackout of stars in a region near the center, the direction near the center of the galaxy, and it's called the coal sack. It's just such a dense cloud of dust. It just blocks out all the light from the stars behind it.
Today, the coal sack lies in the constellation Crux. Crux, commonly called the Southern Cross, is the smallest constellation, and 20 stars are visible. Sailors relied on Alpha and Gamma Crux to locate the South Pole, since there is no pole star like Polaris in the southern hemisphere. As astronomy developed, the scientific community realized it needed to unify the names and shapes of the constellations.
In 1922, a group formed called the International Astronomical Union. They were sort of the political body of scientists assigned to divide up the sky, set up boundaries so that everybody could agree, here are the boundaries. Those boundaries were based on historic constellations.
The IAU adopted most of Ptolemy's original constellations and added more to include every visible star with no overlaps.
Some of them were named more recently in the Southern Hemisphere when Western Europeans got a really good look at the southern skies.
In all, 88 official constellations cover the night sky. But there are other small collections of stars that form obvious patterns called asterisms, like the Little Dipper and Big Dipper. The Big Dipper is made out of Ursa Major's brightest stars. Ursa Major, or the Great Bear, has 71 visible stars. The Big Dipper is recognized by its resemblance to a ladle.
The Big Dipper is probably the easiest object in the sky to find, even if you don't know anything else.
For being such a familiar asterism, the Big Dipper is still full of surprises. The second star in its handle, named Mizar, looks like a single point of light, but a closer look reveals that it's 5 blazing stars. Cygnus, the swan, claims 79 visible stars. A star named Deneb is a thermonuclear powerhouse that forms the swan's tail. At 200 times the diameter of our sun and as much as 250,000 times as bright, Deneb is one of the largest examples of a white supergiant star.
It's a star in a very unusual phase of its evolution. There's very few stars like that, and they don't spend very much time of their lives in such a high luminosity state.
White supergiants are rare because the star is transitioning from a red to a blue supergiant, a phase that only lasts a few million years. This may sound like a long time by human standards, but for a star, it's less than 1% of its lifetime. For a constellation named after a graceful bird, Cygnus bears the scars of a violent past.
So Cygnus is also home to something called the Cygnus Loop, which is a supernova remnant. There was a star that blew itself to bits, basically.
A gaping black hole called Cygnus X1 lies in the swan's heart.
Cygnus X1 is an 8.7 solar mass black hole, so it's 8.7 times the mass of our sun, that's orbiting another star.
Cygnus X1 was the first black hole to ever be recorded.
In fact, we first detected Cygnus X1 not so much because of the black hole, because it's black, it's very hard to see, but because of its effect on its companion, which is this giant star. And in fact, the black hole is slowly devouring the companion, and eventually will probably swallow it up.
And when it does, a constellation will lose a star, and our perception of the night sky will change forever. Our night sky is in constant change. Within each constellation, stars are born, while others are swallowed by black holes. Every supernova explosion, exotic star, and nebula has one thing in common. They are identified by the constellation they're located in. But even before we invented high-powered telescopes to see them, constellations served an important purpose. They brought people the nightly news that they dared not ignore.
It was a question of life and death. You see, the night sky is a calendar. That was the very first scientific invention of us humans, the calendar in the sky.
The rising and setting of the sun, the changing phases of the moon, the seasonal reappearances and disappearances of the stars. People see that there is, in fact, an order to the world. They, in fact, see order in the sky that is useful for them to anticipate what's happening on the Earth. That's a tool for survival.
When you look at the sky, you see these groups of stars that are connected to important events that would prompt you to behave in certain ways, or to move in certain ways, or to plant or harvest.
Besides seeing the pattern of stars changing with the seasons, the ancients made another crucial observation: the shifting stellar canopy. shape their world.
Travelers who went a long way south, for example, from Greece, started being able to see different constellations from any of the constellations that have been visible in their hometown. So it's telling you that you're really moving on a curved surface and changing your perspective.
Today we understand the shape of the Earth and the parade of the seasons. But constellations haven't outlived their usefulness. Instead of telling us about the Earth, they're helping us make sense of the stars.
A constellation is a lot like an art museum. In an art museum, you'll see artists who have used different kinds of materials, painting, photographs, and ordinary objects. A constellation also has similar objects, but made of different materials. Some of them have more helium or hydrogen or carbon, silicon, iron, and yet we can group them together. In both cases, the objects that are gathered in an art museum or a constellation, they're artificial collections that we've put together for some reason.
Like countries, constellations divide the sky into territories.
When you say Orion, I know exactly what part of the sky you're talking about. So to an astronomer, a constellation really is kind of a handy map. It's just a way of organizing things, so we kind of know where stuff is.
And even though the night sky is infinite, we can see only a sampling of stars before dust and distance blocks our view.
You'll probably see on a very dark night maybe 1,500 to 2,000 stars with your naked eye, if you're not using binoculars or anything. So what we're seeing is only a tiny, tiny fraction of what's really out there. That would be sort of like looking at the whole population of the United States, 350 million Americans, and seeing 5 people.
Centaurus, or the Centaur, contains 101 visible stars. 2 of its stars, Alpha and Beta Centauri, are the brightest stars in our night sky. Centaurus holds Alpha Centauri, the star nearest to the Earth after our own sun. And a closer look reveals that Alpha Centauri is actually a triple star system. It's not unusual for stars to share the spotlight with 1 or 2 orbiting co-stars. In fact, it's the norm.
Over 60% of the stars you see in the heavens are actually double stars, triple stars, quadruple stars. Our sun is an exception. Our sun apparently has no companion.
While our sun makes its lonely voyage through space, the stars of Omega Centauri never lack company.
It is the brightest globular star cluster that you can see without a telescope, just with the naked eye, because it is a giant cluster of about 10 million stars.
Omega Centauri is the largest star cluster in our galaxy. These tightly bound stars all have different, complicated orbits, but they still manage to move together as a single group. Where the cluster comes from is anyone's guess.
It's an unusual object, and a lot of astronomers suspect that this might be the center of a galaxy which got eaten, consumed by the Milky Way when it fell in. It certainly happens fairly often that big galaxies are cannibals and they eat little galaxies, and Omega Centauri may be a remnant of this process.
The light from Alpha Centauri takes about 4.2 years to reach us. But when we look at Omega Centauri, we're seeing light that's traveled 16,000 years. That's some indication of how large Centaurus really is. It also shows that a constellation exists only in our mind's eye. And each star, like every piece of art, begs to be explored. The constellations organize the night sky and make it almost comprehensible. As we gaze at the twinkling lights, it's easy to forget that each is one of billions of blazing suns, fusing elements and possibly creating new worlds. Our distance gives us no sense of the star's power. It also gives us no sense of the endless depth of space we're peering into. The flat plains of the constellations are an illusion.
As you start getting away from the sun by several light years, the nearby stars begin shifting relative to the more distant background stars. So the constellations start distorting. And by the time you're out at 10, 20, 30 light years, you probably would recognize few of the constellations. So if you lived on a planet going around Vega, let's say, that's 25 light years away from here, you'd have a different set of constellations in your sky.
Millennia of stargazing have made the grand sweep of the constellations predictable. Our rotation around the sun carries us through their annual cycle. The stars in the constellations are in constant motion, not just as the galaxy spins, but also as each star's gravity tugs and pulls on its neighbors.
The fastest motion of the stars is 150 miles per second. We don't have any man-made object that can go that fast. The random motions of these stars with respect to each other are more like 10 or 20 miles a second, and that is comparable to the speed of our fastest spacecraft. That's, of course, way, way faster than a high-speed bullet.
The stars are always moving, and their distance from us masks their enormous speed. It's like looking out the window of a speeding automobile. The fence posts and trees closest to the highway whiz by, while the distant landscape creeps slowly past. Over our lifetime, in fact close to 1,000 lifetimes, most stars don't appear to move at all.
It just intrigues me to think that if I could find one of our, quote, recent relatives, a Cro-Magnon man, for example, he would probably correct me because he would be more familiar with the sky and he would know the constellations a little bit better than the people do today.
But little by little, our star maps are reaching their expiration dates.
In 10,000 years, the stars would be noticeably different. The constellations would be noticeably different than what we see now. In 500,000 years, they'd be unrecognizable. And if you truly could see a time-lapse photo over a period of 1 million years, you would in fact see stars racing around the sky.
The constellations are a snapshot, a flattened portrait of the night sky. And like a portrait, it's a good likeness, but not the whole story. If we could fly into space and see them from another angle, these old familiar star formations would be unidentifiable. But right here, right now, the 88 constellations provide reassuring guideposts while reminding us of our past.
The constellations really don't fulfill the functions that they fulfilled originally for the people that devised them. For them, there was a direct cause and effect connection between something that was of interest to them and their lives. They watched Sirius because it was a seasonal indicator. We don't use the sky that way anymore, but the story